Today we're going to continue our discussion of non-deterministic log space. So the class NL. And if you recall, what we proved in the last lecture was that path is NL complete. So just as we had problems like SAT and QBF, which captured various different classes, the path problem, which is a very natural problem, recall that the path problem is just G, S, and T, and G is a directed graph, and there is a path from S to T. So path is NL complete. And what we will do in today's lecture and probably the next lecture is have a greater discussion of NL. So a natural question when you think about non-determinism is, can we define NL in terms of certificates? Just as we did it with NP. Like NP can be defined in terms of certificates. Or I should say polynomially polytime verifiable certificates. So let me actually start by giving you an incorrect definition. We'll analyze why it's incorrect, and from that we'll actually we'll get better understanding of certificates, and also then we'll see how to define NL appropriately. So let me start with a naive, and we'll see that this is going to be incorrect. A naive incorrect definition. So I'll say that L is in NL. So this is going to be a certificate viewpoint. If there exists, I'll say a polynomial P and a log space machine M such that for all X in the language, or I'll say it's badly written, so that for all X in 0 and star, X is in the language if and only if there exists a Y where the size of Y is at most polynomial in X, such that when the machine takes both X and Y, it exists. Does this definition make sense? So ignore the first part. I'm just saying that I'm defining a language such that if X is in the language, there exists a certificate that is verifiable by a log space machine. Now, if you recall, what I did for defining NP is if I simply replace this by polynomial time, then what I got over here was NP. And that was the definition of NP. Now, instead, I could replace the polynomial time by log space. The certificate length is still polynomial, which makes sense, right? Because a non-deterministic log space machine can take at most polynomial time, because we know that NL is in P. Any questions about this definition? So this seems like a natural extension, a natural definition of NL with respect to certificates. And, it takes a bit of thought, but surprising, this is actually wrong. This is incorrect. And we'll see why this is incorrect. So this definition is incorrect. And what I mean by incorrect is that it doesn't really capture non-deterministic log space. Such a machine can actually do much more than what we think non-deterministic log space is. Because in such a setting, we can decide satisfiability. By such a setting, I mean this setting. Meaning, given, and instead of sat, let me just think about a 3CNF. So I'll just say 3SAT. Given a 3CNF phi and a possible assignment, y. So I'm going to use y as the possible assignment because y is the certificate. We can check if phi of y is equal to 1 in log space. Okay, we can actually verify that the certificate is correct in log space, and let me show you why that is the case. And it's something that you probably would you wouldn't be surprised once you see the construction. So here is M, the machine. Now the machine takes as input, I'm just going to put the certificate y1 up to y, let me not use the word n, let me just say k, because there are k variables here. And then over here you have phi. Right, so you have phi. And you have these various clauses here. So you have C1, C2, up to Cm. And each clause is something like xi or xj, or xi prime, the negation of x prime, so on and so forth. The certificate says set xi to the bit yi. And of course it has its workspace here, but this is only of length log n, and n is of course the length of this. You could also imagine n being the length of, can be at most, k is at most n. So for each ci, machine has to look up the value of the literals in that clause and check if ci is satisfied. Right? That's what the machine has to do. It has to look up the values of those literals and then just check if ci is satisfied. The machine can count, right? Because it has log space. So for any clause, it can look up the indices. It can look up the indices of these literals, and then the machine can sort of walk through over here, get the appropriate value, and then just check if any of these values is going to satisfy the clause. Okay, so is this clear? And it only needs machine only needs log space to look up these values. Right? Because all it has to do is it just has to store the index from 1 to n. Is this clear? Any questions about this? So you see why in this definition, when I replace the standard NP definition, when I replace the poly time by log space, I don't get NL, it actually looks like I'm getting NP. Because such a machine which uses log space, right? So I'm just going to get rid of that. A log space machine, a log space verifier is enough for 3SAT. If you think about it, a log space verifier is enough for clique. Because if you gave an adjacency matrix and you gave a potential clique, a subset of vertices, a log space machine can go and look up whether all those edges are present. Any questions about this? This is a very important point.
Is this almost indicating that if we use this definition, P would equal NP?
I mean, if you use this, in some sense, yeah, if you use this definition, it would actually suggest that NL is NP, which is even more than P being NP. Would say that NL is NP. But I think that I think the way to look at it is not that it's saying anything about P versus NP, but rather that when you transform this notion of a non-deterministic machine into a certificate viewpoint, you have to be careful. Like, you have to prove that this definition is the same as the other definition being using a non-deterministic log space machine. I mean, technically, this isn't really, because we have already defined what NL is. This is not a definition, but rather this is a theorem. This is saying that this is an alternate characterization of NL. Like, that's the theorem. And that theorem, I wouldn't say it's false, because we don't know. Maybe it is true, because NL could be equal to NP. And if NL was equal to NP, then of course this would be true. But assuming that NL is not NP, the statement is false. So you're right that it is in that sense related to P versus NP. But I think, to step back, a way to think of it is, it's not the right characterization. It's not like sort of a direct characterization. If the statement was true, it would be a highly non-trivial, complicated proof. That makes sense. Whereas what you expect if you have two different characterizations, at least at this level, is that you would say, okay, so one should follow from the other fairly easily. And we'll see that there is a viewpoint with certificates that follows fairly easily. It turns out, now I'm not going to go through this proof in great detail. I'm just going to sort of write this here. By carefully looking at the Cook-Levin theorem, or technically the Cook-Levin reduction, one can show that for all languages in NP, L can actually be reduced in log space to SAT. Remember, previously, you look at the Cook-Levin theorem, you say, oh, you can reduce in polynomial time. But actually, if you look at the proof carefully, you can do it in log space. That is, the reduction shown there can actually be done in log space. Indeed, in this definition, instead of saying NL, this is actually just saying NP. So what this is saying is whether you put a polynomial time machine there or a log space machine there doesn't matter. It's still NP. You don't need the verifier to be polynomial time. A log space verifier suffices. Of course, the proof of this is non-trivial because you're using the Cook-Levin. You're using Cook-Levin there. So I'll just write this. Just write this carefully. So I'll just state this as a theorem. I'll say L is in NP if and only if there exists a polynomial P and log space machine M, such that for all x is in L if and only if there exists Y, the length of Y being at most polynomial X, such that M xy accepts. And if you sort of walk through all the reductions that we have done, they all turn out to be log space reductions, even though we've just said they're polynomial time reductions. By digging into them a little bit more deeply, we can actually show that they are log space reductions. And I'm not going to prove this, but let me just sketch it out. Now, if you recall, essentially how does the proof goes? It goes by this sort of Tableau method, right? So one would basically construct the tableau. And so one has these variables. So we're going to construct, so this is x is the input. We're going to construct a phi, and we're going to have these variables z t I, which is sort of z. There was sort of z t I. I believe there was also a character like alpha, right? So this is indicator that at time t, the ith symbol on the tape is alpha. There was some long-winded construction. It's a long-winded construction, and so the final phi that you get basically had these things that it was called unique, meaning that for any value of t and I there should only be one alpha where this is true. There was some start, and there was accept, and there was move. Well, there were sort of all of these Boolean formulas that were written down to encode that the Turing machine behavior is what it should be. That there is a way of filling in the tableau consistent with the Turing machine behavior. It turns out for each of these, if you look at it, it's built up into these little clauses, and each clause would potentially only depend on a few symbols, on a few cells. So all the log space machine needs to do is to be able to count, which it can do. Right, so I'll just say that the individual clauses in phi only depend on a constant number of variables, and only the starting configuration depends on the input. So if you walk through it somewhat carefully, what you can observe is that actually it's a log space reduction. The final formula can be computed implicitly in log space. Okay, any questions about this? This is this is sort of a deep point here. Even though I haven't sketched out the proof, I don't think the proof is as important as you understanding the overall idea here. Questions?
Slightly deviating from the proof that you're talking about, but the theorem as a whole, is it? I was kind of thinking like, so NP completeness in the language of log space reductions and polynomial time reductions is, we don't really know. That's like basically the same question as NL vs NP, I guess.
Or I guess whether L is equal to P in that case.
Okay.
Right, because you're saying are log space reductions the same thing as polynomial time reductions? Now, if L is equal to P, then of course that would be true.
Okay.
And if L is not equal to P, then potentially that's not going to be true. I think you could probably come up with a construction, although I don't immediately see that, but so the point that I'm making here is simply that all the reductions that we've done so far actually turn out to be log space reductions. So this isn't proving that log space reductions are the same as polynomial time reductions. This is just saying that it so happens that by carefully looking at the reductions we have constructed, what we have is that that all the reductions that we have done are log space, and therefore our entire theory of NP completeness, we can replace polynomial time by log space there, and whatever we have has not changed.
But we don't know if if all polynomial time reductions can be log space.
No, we don't know that. We
just have seen that it happens very often.
Yes, we've just seen that it happens whenever we do this, and therefore log space seems to be enough to give us this notion of NP completeness. But definitely this is true, right? So it just says that all languages can be reduced in log space to SAT. So, in some sense, my guess is, because all languages can be reduced in log space to SAT. Like, that's just true. So, at least what this says is with respect to satisfiability, and actually you can also argue that if you look at Cook-Levin, what you'll get is a CNF, and you can convert that to a 3CNF. So, you can convert any language in log space, you can reduce any language in NP to 3SAT in log space. So it's saying that you have this lens of polynomial time, but even with a more sort of smaller lens of log space, you basically get the same sort of structure. Which is kind of surprising when you think about it. It actually so happens because of the way the Cook-Levin reduction works, and when you dig into these reductions, you recognize that there's basically it's locally computable. I mean, so I have to be careful. It's not locally, but you get what I mean. Essentially, that any bit or symbol of the formula can be basically computed in log space. Questions? All right. So now the question is the right definition. What is the right definition? So we'll define a tape to be read once if the head on that tape cannot write on the tape and the head only moves right. So you just think of it as move in one direction. So what it says is a read once tape. It's a special kind of tape where the head starts here and the head can only march forward. I mean, it can decide to stay or march forward. The head cannot move back. So it's almost like there's this text here that you get to read once. You can never go back. All right, any questions about that? All right. And so it turns out that if you put the certificate on a read once tape, then what you get is NL. So L is in NL if there exists a polynomial. I'll say if and only if, and I'll state this as a theorem because we'll prove it then. A polynomial P and log space machine M, such that for all x is an L if and only if there exists a certificate y such that y is of polynomial length, size, such that M xy accept. So this is what we had before. And by itself, this was NP, not just NL. Such that M accepts and X is on the input tape and Y is on a read once tape. So you should think of this machine. It gets its input X. This is read only because it's the input. Then it gets a certificate Y. And this is read once. And then, of course, it has its workspace. Okay, does this make sense? So the certificate, this is also called a read once certificate. It's a read once certificate. So it means that you get to read the certificate only once. Remember, let's go back to our example with 3SAT. If you look at the certificate, which is the Y's, the head has to move back and forth because for every clause there are 3 variables, and so the machine may have to go back and look at a variable that it saw before, a variable value that it saw before, because the same literal may appear multiple times. So the head has to go back and forth. What we impose here is to say that it can only be read once. Suppose instead of this I said polynomial time machine, but the certificate is still read once. Then what happens? Okay, first, before I proceed, do you understand the statement of this theorem? And we'll come back to proving it shortly. The proof is actually not that, it's quite easy once you write things down. But does the statement make sense? So a language is in non-deterministic log space if and only if there is a log space verifier and the certificate is read once.
So the only difference is that the certificate is read once. essentially.
Exactly.
Okay, gotcha.
Okay, so I'm going to write some things down here so that we can understand. So I'm referring to this machine as the verifier, remember, right? So you have log space verifier, sort of standard certificate, meaning that not read once. So standard, again, it's all polynomial size. This we said log space verifier standard certificate, this was NP. When we did polynomial time verifier standard certificate, this is also NP. Okay, so let me draw this out in this way. So here I'm talking about the certificate. Is it a read once certificate, or is it a standard certificate? And here I'll say, so this is the certificate. And here I'll talk about the verifier. Is it log space, or is it polynomial time? And here I'm talking about the verifier. Right? So what I'm saying is a log space verifier with a standard certificate, that's NP. And so a polynomial time verifier with a standard certificate, that was also NP. What about a polynomial time verifier with a read once certificate?
That is NL.
This is NL. No, so I said this is NL.
Oh.
Log space verifier with a read once certificate. This is NL. I have to prove this. This I need to show you, but I will show you. What about the polynomial time verifier with a read once certificate?
I believe this is NP2 because of the closure of polynomials, because you'd read each. You could just have multiple copies of that same certificate. There's a polynomial number of copies of it, so even though it's read one, you can just keep going down the line and technically access it again. If that makes any sense.
Almost, yeah, you're almost there. You're right that this is NP, and the proof is actually, it's much simpler. So because it's a polynomial time machine, the first thing it can do is actually read the certificate and copy it onto its workspace. At which point it can do whatever it wants with it. Right? So the polynomial time verifier can just copy the certificate onto the workspace. A log space machine cannot copy the certificate. Read. So this is read once, this is read only. That's the whole point of a log space verifier, right? It cannot actually it can read through the certificate, but it cannot store the certificate. So M cannot store the certificate in the workspace. On the other hand, this is NP simply because the certificate can be stored in the workspace. And now the certificate is not read-only. Now the certificate becomes a standard certificate. Does that make sense? Because it actually has enough storage to store the certificate. So it stores a certificate, then it does whatever it wants with it. So the fact that it's read once is not a restriction for a polynomial time machine because it has enough space. It is only a restriction for a log space machine. because a log space machine cannot afford to store the certificate. So hopefully this picture makes sense. Please ask me any questions. So let me pause here and I'll take any questions that you have about this before I tell you the proof of this theorem, which, as I said, the proof is not very complicated. So let me prove this theorem. And the proof now, it's not that complicated. You basically write everything down carefully and you observe that the non-deterministic log space machine can be simulated in this mechanism. One of the reasons that I gave you this picture here is to show you that you can actually ignore the notion of standard certificates, at least from this perspective. You could just assume that all certificates are read once, because even for NP, you're doing read once certificates. Anyway, so let me give you the proof of that theorem. So let's start by saying, suppose L was in NL. So, there is a non-deterministic Turing machine running in log space that decides L. To get the verifier certificate viewpoint, so let me call this machine M. Let the certificate be the non-deterministic choices of a run of M. Right? So you can think of it as the verifier M prime simply runs M using the non-deterministic choices in the certificate. Essentially what this is saying is that M never needs to look back at previous non-deterministic choices. So if you think of the running of M, the non-deterministic log space machine, it just goes ahead and makes non-deterministic choices. It doesn't really need to remember all the choices it's made so far. It's just making those choices and then it writes down whatever it wants in log space. And so you can simulate that just by a read once certificate. Indeed, this is the key. The key is that a non-deterministic machine never needs to look at the past, right? Because it just keeps making its choices. It can write down whatever it wants in its workspace, but it only has logarithmic workspace. And so a log space verifier can clearly simulate M using the non-deterministic choices in the certificate. Right? So this proves one side of our theorem. It proves that if, well, I guess technically it's proving the only if side. Sorry. Or whichever way you want to say it. I was just saying that this is saying that if L is an NL, then there exists this sort of log space machine with a read once certificate. Right? And the certificate is read once, so this is fine. Does this make sense?
Kind of a dumb question, I guess, but why do we know that M runs in polynomial time? Like, how do we know that there is a polynomial number of non-deterministic choices?
Good point. No. So that's a good point. So remember, so why is it that the number of choices is polynomial? If you recall, you know that a log space machine is in P. Because L is in P. So a log space machine can never run more than polynomial time. Any log, whether it's deterministic or non-deterministic. Because if it runs for more than polynomial time, then it's cycling. And it's an infinite loop.
Gotcha. Okay. Thank you.
Right? And so this is worth writing down, that the certificate is poly n sized. Because sort of L is a subset of P, basically. Okay? The other side is even easier. It's just it's pretty straightforward. And this is just saying that, consider L with a log space verifier and read once certificate, and I'll refer to this as M prime, just to say that M prime is a verifier and M is going to be the non-deterministic log space machine. Create a non-deterministic Turing machine M that simulates M prime and uses non-determinism to guess the next symbol of the certificate. Right, so this is even easier. So then we know that M prime decides L. That ends the theorem. It's pretty straightforward. It basically says that if there's a certificate that's read once, then your non-deterministic log space machine just guesses the next symbol of the certificate. At any point, it can simulates M prime using and the certificate using non-determinism. And on the other side, we simply argue that a read once certificate is pretty much the same as non-determinism. So maybe the whole point of this exercise is to say non-determinism is really the same concept as a read once certificate. It just so happens that when you have polynomial time, whether it's read once or not doesn't matter. But let me write that down over here, and I'll just say that read once certificates are sometimes morally the same as non-determinism. And then that's sort of the main message. And therefore what it says is, if you're trying to understand non-determinism, you should look at read once certificates. And then you get non-deterministic log space and non-deterministic polynomial time based on the power of the verifier. Okay, questions? Does this make sense? Okay. I want to move on to another topic now. So if there are any questions, please stop and ask me. And if something is not clear, please let me know. So now we're going to come to, now that we've understood NL from multiple perspectives, we know that path is NL complete, and we know how to characterize NL in terms of certificates. We are now ready to prove our big theorem, which is the Immerman-Szelepcsenyi theorem. And this proves that NL is equal to co-NL. Complementation actually does not change non-deterministic space classes. And generally, one can do this by a padding argument. Non-deterministic space of Sn for any function S is the same as just the deterministic, not the non-deterministic space Sn for all Sn that are greater than log n. I should say, it's for all Sn that's omega log n. So essentially it just says that for any space class, and log n is sort of the smallest space class, so one can do this by a padding argument. Could do this by a padding argument. Right, one can just sort of pad the input enough so that the space becomes much smaller with respect to the input size. So NL is equal to co-NL. This is a big theorem in computational complexity theory. It was a surprise when it came out, because people thought maybe complementation seems to change classes, just like NP is different from co-NP, or we believe it's different from co-NP. But remarkably, NL was different from co-NL, and that's how space complexity seems to behave in a very different way from time complexity. Okay. So how does one prove this? And we're going to use sort of all the tools that we've built so far and use them as part of the proof. So remember, we said that path is NL complete. The complement of path is co-NL complete. One can show this. This is not, I think there was an exercise in the first homework where you did this for NP completeness, and the same argument works for NL completeness. So if we show that the complement of path is in NL, then we prove that NL is equal to co-NL. Right? I'll leave this as an exercise. So show this statement. Show that if path complement is in NL, then NL is equal to co-NL. Okay, so what is the complement of path? So it's the encoding of a graph, a source, and a sink, such that G is directed and there is no path from S to T. So you recall that path being in NL is is obvious, or it was easy to show, and that's because the non-determinism just tells you what the path is. But how can non-determinism tell you that a path does not exist? Because the non-determinism, or as we said, the read once certificate is the path. But how can non-determinism prove that there is no path? And this in some sense is the brilliance of the proof, which shows that actually you can come up with a read once certificate for the non-existence of a path. And so let's see why this. Let's sort of dig into the details of the proof. And I might not be able to complete today, which is fine. So I'll do as much as I can today, and then we'll continue with the proof in the next lecture. So I'm going to walk sort of slowly through this construction. We're going to prove that the complement of path is an NL. And we're going to think in terms of read once certificates. Read once polynomial sized certificates. I mean, really, you'll go nuts thinking of a non-deterministic log space machine. Okay, so we're going to think about read once certificates. And as we have done in the past with a lot of space complexity, we're going to define the following language, which is just GST. As I said, there is no path from S to T of length at most I. Okay. So let dst be the shortest path distance. From S to T. So path of I is just saying GST, so the distance, the shortest path distance is strictly greater than I. And if you think about what the path of n is the same as path. Because if the shortest path distance is more than n, then obviously there cannot, you could even probably do, I think, maybe an n minus 1, right? Because if the shortest path distance is more than n minus 1, then obviously there cannot exist a path. So what we're going to show is sort of a hierarchy of hierarchy of read once certificates. We'll show that if you have a certificate for path I, then you can start building certificates for path I plus 1. So the idea is we will use certificates, again these are read once, for path complement I to construct read once certificates for path complement I plus 1. And this idea is also known as iterative counting. And you'll see how, why we're doing iterative counting. So let's start simple. What is path complement of 0? What is path complement of 0? What is this language?
That means that, well, that's just there is a path at all, right?
No, it means that when, okay, so maybe when do you accept S into what is the language specifically?
Well, the language is the paths from the language are the nodes where there is no path from S to T of length less than equal to 0, right?
Okay, and what are those pairs? So when is there a path of length 0 between two vertices?
Well, there's a path if there's a path between S and T, right? That path would be greater than 0, right?
Right. So, but indeed, what you can, this language is exactly, okay, so let's ignore G because G is fixed. This is the language exactly of pairs S comma S. Because the distance of S to itself is 0. And so this path complement of 0 is exactly, so I'll write this down, GST, where S is not equal to T. Is that right? Because when S is equal to T, then actually the distance is 0. Otherwise, the distance is non-zero. Just to be clear, right, we'll say that if there is no path, we're saying the distance is infinity.
Okay.
I should say that.
So there is a path between every node.
Between every pair, there may not be a pair. There may not be a path from S to T, but that means that the distance is more than 0.
Oh, sure.
Right. So the shortest path distance is infinity if there is no path.
Okay.
Right. Maybe I should just recall the distance is infinity if there is no path. Right, so path 0 is basically just checking that the source and the sink are different. That's it. So this is actually pretty easy to check. This is in log space. Right? You just have to check. A log space machine can just go and it can just read all of S into its input and just go in the workspace and just check. Right? Okay, so what is path 1? Complement.
Well, that would be any two nodes that are not direct neighbors, right?
That are not neighbors, right? So what you say is that S is not equal to T and ST is not an edge. Right? I'm just thinking if G is equal to V comma E. Right? That's what this language is. ST, I'm sorry, is not an edge. what about this language? Is this in... Can you say something about this language?
I think that's also in log space.
That is also in log space. Why?
Because you can just check whether or not the two nodes have an edge, right?
Have an edge, right? You could just go and look this up. You can imagine G is stored. Let's say G is, and we said we could imagine G is stored as an adjacency matrix, right? So let's just say suppose G is an adjacency matrix. Then this is just single lookup.
Right.
Single lookup in G. Okay, so that's also in log space. Okay, good. Now let's move on to the next one. This is trickier. So this is exactly the language, GST. So the shortest path from ST is at least 2. Now this is not a lookup. This is not a lookup. So let's try to understand how are we going to certify? How are we going to certify in a read one certificate that the distance between S and T is actually more than 2? So here's S and here's T. And let gamma plus of a vertex, this is the out neighborhood, and gamma minus of V is the in neighborhood. So what is the condition of this? Is the same thing as saying gamma plus of S intersect gamma minus of T is the null set. Right? That's what it means. It means that you take its neighborhood here, which is the out neighborhood, you take the in neighborhood here, they're disjoint. Because if there's anything in common, there's a path of length 2. I'm just going to write this out. There's another way. I'll just say that dst is greater than 2 if and only if for all vertices V in the out neighborhood of S, Vt is not an edge. Okay, this can be checked in log space. This can be checked in log space. So now this seems to be telling us what the certificate would be. What would the read one certificate be? Can you now hazard a guess based on this? This is a first try. First try. The certificate is gamma plus S. So the certificate is V1, V2 up to Vk, where all of these are neighbors. So this is what the certificate is. We need to check that the certificate is actually correct. We need to be able to validate through a log space machine. So let's see what the verifier does. The verifier can just go through each of these, right? So it's going to say for V in v1 to vk. First step is check if SV is an edge, else reject. Right, because then that means the certificate is faulty. It expects the certificate to exactly be the neighborhood. Then check if VT is not any, else reject. Right? And finally, once it reaches all of this, it can just accept. So it goes through everything in the neighborhood. It goes through everything that is supposedly part of the neighborhood. And remember, this is read once. Because it's a single for loop that's just going over each of these vertices and checking is SV in, so here's S and here's T. So you're given some vertex V, you check that this edge is present, and you check that this edge is not present, and then you say okay. Because if this edge is present and if the VT edge is present, then there is a path of length 2, so it can reject. Because it is trying to accept ST at distance at least 2. There is a problem with the certificate. What is the problem with the certificate? Okay, I want you to think about it. So there is a way in which there is a certificate that might fool the verifier, meaning that it could go through the certificate and accept, but actually there is a path of length 2. When can that happen?
Well, do we check if S and T have an edge?
Sure. Okay, we can check if S and T have an edge. So you're right. So we'll say check ST is not any. But yes, but that's not the problem. There's a bigger problem. So you're right. I did omit that. Yeah, there's a bigger issue.
Are we checking that all edges are adjacent?
Which edges?
As we traverse the path.
So there's no path, right? You're basically going over all the neighbors. And you're just ensuring that they're neighbors of S and ensuring that those vertices, T is not a neighbor of those vertices. So you're checking this condition here, up here. If you look at this condition, is this verifier effectively checking this condition, the verifier in the certificate? Remember, this verifier, like it has to think of the way that think of this verifier. To give you a picture, is basically there's this massive graph here. And then there's this like really small verifier because all it has is log space. And it's getting its certificate over here. So it's reading through the certificate. And then what it does is it basically goes and queries the adjacency matrix. And it's going and looking up. It says, okay, so here's some vertex. Okay, is this an edge? Yes or no? Is there an edge here or not? That's all it's doing, right? While it's reading through all of this. This verifier cannot even afford to store the graph. The graph is massive. The graph is massive. So what is the certificate missing? What is the certificate missing? Let's walk through this step by step. Is it checking this condition correctly? when it gets a V? When it gets a vertex, so when it gets a V, is it checking this condition correctly?
I think that's correct.
Yeah, that's correct. For any vertex V, is it checking this condition correctly? Whether V is in the neighborhood.
Yeah, right, because if there's an edge, then it'll be in the neighborhood,
Right, so it's checking both of these conditions correctly. What is it missing then? So you look at this, it's getting both of these correct. What is the third part to this? If and only if what? You see, there are three parts to this. I've put my finger on each of them. Which one is it missing?
Is it not checking every V?
It's the for all, right? Because how does the verifier know that there isn't a neighbor in the list?
Oh.
What if there is a neighbor, but it's not there in the certificate? There's no way the verifier is going to know. And it's read once, so it can't go back and check. Right? So here's the tricky part, right? What if there is some neighbor, I'll call it V prime of S, that is not in the certificate? I mean, so the verifier can loop over all neighbors of S, but it cannot go back and check if they lie in the certificate. You see, because once it goes through the loop, it's read through the certificate once. It can't go back and check if it's missing a vertex. So it doesn't.
So it just has to trust that the certificate contains all the neighbors. It doesn't know for sure.
Exactly, but that's a problem. But in our model of certificate, you don't trust the certificate. You have to be able to verify it. So if the certificate is false, the machine has to be able to reject it, even though it's read once. So it gets the certificate, only gets to read it once, and it has to say in the end, yes, the certificate is correct or not. You see how difficult this is for a log space machine. So what is it? Can you add something to the certificate that is going to convince this vertex, could convince the verifier that the certificate is correct? What could you add? Remember, it is guaranteed that everything in the certificate is a neighbor. What piece of information could convince, small piece of information could convince the verifier that these are all the neighbors?
Is there any reason why we can't just have all of the vertices in the certificate?
You could have a polynomial size, but if you have all the vertices in the certificate, it's going to end up rejecting it because it's going to find something that's not a neighbor.
Oh, right.
Right, so the way you've set it up, it should only have the neighbors.
Could you say that of the size of the
Okay,
certificate?
good.
Or the size of the number of neighbors in the certificate?
Okay, good. So exactly. So what you could do is the certificate could also contain the degree, the out degree. Because you know that the verifier can count. So suppose the first thing it got was actually the degree, the out degree. It goes and checks if that is the out degree. That it can do just by counting the number of neighbors in the input. So it does that count and then it goes and checks. So I'll write this down. So the certificate it's of the following form. First, it gets what I'll call dv plus, which is the out degree. Then it has v1, v2 up to vk, and v1 is going to be less than v2. This is to prevent repeats. Okay, so this is what it wants the certificate to be. We have to make sure the verifier will not get fooled by an erroneous certificate. Okay, we want to make sure that it's not going to get fooled by an erroneous certificate. So now let's look at what the verifier does. Step 1, store dv plus from the certificate in the workspace. Right, that it can do, because each of these is only log n bits. Compute out degree of v, check if it matches the certificate, and if not, reject. And then what it does is for v in v1, v2 up to vk, it does its old thing. So first it checks that the out degree is correct, and once the out degree is correct, it can then go and look through each of these. Does this make sense? Any questions about this?
Wait, but what if dv is also a lie?
I'm sorry, dv is what?
What if dv is also just the incorrect number of neighbors?
Is incorrect?
Yeah.
But then it would know.
Consistent with the actual v, with all the v's.
But then that it's checking.
Right. But what if, dv is 5 and then there are 5 v's, but then the actual number of v's is 6? Is that possible?
No, because it's actually going to compute the out degree. The machine can compute the out degree. This it can do, right? Because it can go through the adjacency matrix and just go and see how many ones there are in that row.
Okay.
So dv, actually technically you don't even need this to be part of the certificate, because dv plus can be computed. But it's useful to think of this, because we're going to come to this. This is the way we want to think about it. The certificate actually is going to have a count. And that's why the iterative counting. So the count is important. It needs to know the out degree, and then it says, okay, so it can compute the out degree and check if it matches the certificate. So it cannot be fooled, because if it gets an incorrect out degree, it's just going to reject.
I see.
If it gets an incorrect out degree, it rejects. When the degree is correct, then it can do this. And then at the fourth step, it can ensure, check that k is equal to dv plus. right? And if not, reject. Because it can count, it can store a constant number of counts. So it's going to store the degree. It's going to store the degree. And once it has the degree, it can just ensure that, okay, it's only going to see that many vertices. It has to see that many vertices. And for each vertex, it is verified that this is indeed a neighbor and it is not a neighbor of T. Right? So, just to give you the picture, it knows how many vertices there are. The log space machine knows how many vertices there are. And it is also going through these in increasing order, which it can check. I can just check that this is an increasing order. And then for each of them, it just checks that this is not present. And because it knows how many vertices there are in this set, in the neighborhood, it can sort of, the certificate is correct. So the punchline is that there exists a read once certificate that is log space verifiable of the distance between S and T being greater than 2. Okay, so the point is there exists a read once certificate of the distance being greater than 2. And we're going to build upon this to sort of get the full read once certificate for the complement of path. This is a good point to stop. So I'll end the lecture here and I'll take any questions that you have.